In this problem, we're going to find the magnitude and direction of force P, and we're given this system, this mechanical system that contains two pulleys and a weight C, or a mass of weight of C. Okay, so what we're going to do, we're going to draw a free body diagram. That's usually the first thing you're going to do in all these problems. And the point of interest is not necessarily the ropes that are connecting to C, because that's arbitrary, but actually the tension forces between the pulleys and this force P and this tension force that is created on this pulley because of this weight C. So what we're going to do, we're going to draw the free body diagram of this pulley. So let's start off with that. So I'm gonna draw it right here. So we have the pulley itself, and we're gonna walk around this pulley and see what interactions occur. So one important thing that is stated in this problem, that this is in static equilibrium, meaning that this pulley is not rotating or anything. There's no ideas of torque being applied to this pulley. So that's one important thing to note. So with that being said, the tension forces on this pulley are equal to the magnitude of this force P. So what we can say is that this force right here is P at some angle theta. And what we're going to do, we're going to cut here, and cut here. So that's one important thing we're going to do. So this is going to this side at this angle from the angle, so that's P. And then this is parallel to that at some distance right here, and that is P. And then finally we have the weight force being applied to this pulley. So we have a weight force going down like this. Since these forces are parallel, this is given in the problem, so this is parallel to this tension force right here. So these two forces right here are parallel. We have to find the angle between them. So what's nice about this, they give us the distances between the two pulleys in the vertical and horizontal direction. So what we're going to do, we're going to solve for that angle. So we're going to have some triangle created like this. So we have that, and then this is H, and this is D. So we're looking for this angle, which we're going to call alpha. So alpha is simply the tan inverse or arctangent of H over D. And now we could define that. So this is alpha, and this is alpha. So now that we have the angles and we have the free body diagram, and we understand this is in static equilibrium, we can apply the concepts of the sum of the forces, the vector sum of the forces equals 0. So we have to find P and theta. So we have to do this. So sum of the forces in the x direction, that will be P cosine of theta minus 2P cosine of alpha equals 0. And then we get the sum of the forces in the y, which is P sine of theta plus 2P sine of alpha minus WC. And again, we have a system of equations, so we could solve this in the way we solved in the previous example. So we know that P equals P cosine theta equals 2P cosine of alpha, which is interesting because it gives us the ability to define this angle. So we could define theta because cosine theta equals 2 cosine alpha. Since we know alpha, we could find theta simply by doing the arc cosine of that. So that'd be 2 cosine of alpha. So we could plug that in and see what we get for theta. After plugging in my calculator, I calculated for alpha right here, and I got 72.646 degrees. And then after plugging this value of alpha into this equation, I got theta equals 53.377 degrees. And again, I stored these values in my calculator so I don't have any rounding errors. So now that we have theta, we can now solve for P. So what we can do is use the second equation because we know theta, we know alpha, we know WC. The only thing we don't know is P. So that means we have one equation, one unknown, so we can solve for P. So let's do that. So we could define P as P sine of theta plus 2P sine of alpha equals WC, and then we could factor out P and divide by what is left over. So P would equal, P would equal sine theta plus 2 sine alpha, this whole thing divided by WC. So we could plug in some numbers. So I believe WC is 200 kilograms. So we're in the metric system, so we got to account for the weight. So force equals mass times acceleration. The weight force is defined by the weight equals the mass times the force of gravity. I mean the acceleration of gravity. And since we're in the metric system, G equals 9.81 meters per second squared. So that's the value we're going to use. So we said it's 200 kilograms times 9.81. So this is a Newton. And we could plug in these values of theta. And the units come out correctly because the sine functions are dimensionless, and 2 is dimensionless as well. So we're just multiplying by a constant or dividing by a constant. So that's what we're doing. So we define alpha as 72.6. Oh, well, this will be 53.377 plus 2 sine of 72.646. After plugging into my calculator, I got 723.575 newtons. And what we wanted to find is the position, the magnitude, and direction. So they don't explicitly say we have to find the vectors. So what's a sufficient answer, in my opinion, is you just simply say P equals, or the P vector is 723.575 newtons at, let's see, what was it, 53.377 degrees from positive x-axis. And I forgot to define my coordinate system. I'm probably going to do that quite frequently, but it is assumed we're using a right-handed coordinate system. So this is x and this is y. So we define the positive x-axis and to the right. So what a sufficient answer would be that P is a force of 723.575 newtons at 53.377 degrees from the positive x-axis. So that is a sufficient answer. And let me do a quick review of how we solved this problem. So we looked at a free body diagram of this pulley A, and figured out the ideas of tension, and we cut the tension ropes, and then we applied the idea of internal or reaction forces. And we recognize that these two tension cables are parallel, so we could find the angle by using this right triangle, given the dimensions of the problem. And then we apply the other forces that are occurring on this free body diagram. And then we found the angle of theta, and then we found the force P, and we defined the force as a magnitude and a direction by describing the angle from the positive x-axis.